Okay, we have a second equation, second problem with equilibrium. This time we have a ladder or boom situation. So here we have a uniform bar that is suspended at an angle. So here's a hinge, and we have a vertical wall. We have a horizontal cable, and we know the length of the bar is 2.8 meters. Its mass is also given. There's no load, but we can also put some load on it. And we also know there's a 38-degree angle. Okay, so first let's draw all the forces out. So the hinge exerts forces as we discussed before. So starting with the horizontal force from the hinge. So horizontal force. And then we also have a vertical force. Then the bar feels gravity. So let's see, 1, 2, 3, 4, 1, 2, 3, 4. So roughly here is the center. Gravity. And we also have tension from here pulling toward the left. Okay, so just these four forces. So now let's pick axis of rotation. Last time we picked the hinge. We also picked another location. So we can also pick the hinge again and just see what happens. So if we pick the hinge, then these two forces will be going through the hinge. They don't have any torque. So they don't have any lever arm, so they don't have any torque. And then we're left with two forces having torque. So that's not a bad idea. These two unknown forces have no torque. This is a known force. Okay, so what if we moved our axis of rotation over here to this point? So then tension will have no lever arm and no torque. And we have three forces, and three forces they all have torques, and the two forces are unknown, so they're involved in one equation. You cannot solve that rotational equilibrium equation by itself because these two unknown forces are both involved. So maybe this is still a better choice at a hinge because we only have one unknown force, tension, having a torque. So let's pick this axis of rotation right here at the hinge. So axis of rotation at a hinge. Okay, and let's draw lever arms. So lever arm from gravity, we extend gravity. I'll just draw in black. Okay, this is gravity's line of action. Interesting. If I just draw something, it sometimes just goes underneath, sometimes it does not. Okay, so the distance between this line and that axis is this right here. So this is L gravity, and this L gravity it's got this angle involved, 38 degrees. It is adjacent to the angle, and this is the hypotenuse. It is half of the 2.8, so this is 1.4 meters of hypotenuse, and adjacent. So we'll have lever arm gravity is 1.4 cosine 38 degrees, and that is 1.10 meters. And lever arm for tension. So tension's line of action is this. Okay, so tension line of action with axis rotation has this distance. This is the vertical distance right here. So this is the lever arm. I'm just trying to draw besides all these color lines so we can still see this line. So this is lever arm tension, and it is in this larger right angle triangle. So the larger right angle triangle has the whole length of the bar as hypotenuse, and again the lever arm is this time is actually opposite. So we'll have lever arm tension full length 2.8 meters, then times sine of 38 degrees. So we have 1.73 meters in length. And let's see which torque is positive, which torque is negative, starting with gravity. So with this axis rotation, gravity tends to pull down the right end, making this clockwise rotation, so it's negative. And tension, on the other hand, tries to pull this end up, and that makes this counterclockwise rotation. So tension has a positive torque. Oops. And we can use net torque equal to 0. So gravity is minus mg lg. Tension has torque. Tension L tension equals 0. So that gives us tension equals mg lg divided by L tension. M is 14.5, G is 9.8, gravity is lever arm is 1.1, and divided by lever arm tension 1.73. So we can solve for tension. Tension is 90.5 newtons. Okay, so now that we solved the rotational equilibrium, we continue on with translational equilibrium. So we will need a free body diagram that is not too hard. We'll draw it over here. So we have an x-axis and also y-axis. We have gravity down. We have tension to the left. We have horizontal hinge force to the right. We also have vertical hinge force up. This is easy. All the forces are along x or y axis, so these two must be equal to each other, the force of tension and the horizontal hinge force. And these two, vertical hinge force and gravity, they must be equal to each other. So it's really easy. Net force x equals horizontal force minus tension equals 0. We already have tension, so horizontal force is equal to this exact quantity, 90.5 newtons. And then net force in y, vertical force from the hinge minus gravity equals 0. So F vertical is mg 14.5 times 9.8. So use your calculator. We have 142 newtons. Okay, so now we have all the forces. The question asks for tension. It also asks for the hinge force and the angle with the horizontal. So let's combine the hinge forces to get a total hinge force. This is equal to the horizontal component squared plus vertical component squared, square root. So it's 90.5 squared plus 142 squared, square root. And the answer is 169 newtons. And what direction then? Well, let's move on to the diagram here. We have an idea, so here, not to scale right here. This is that hinge force. The combination of, the vector combination of F horizontal and F vertical. So we want to know this angle. And this angle should be related to vertical and horizontal. So vertical is this opposite, horizontal is adjacent, so we can use arctangent. So this angle is arctangent vertical hinge force over horizontal hinge force. So that's arctangent 142 over 90.5. Angles 57.3 degrees. Okay, so the answer is out. I just want to make a comparison. This is the hinge force, 57 degrees, and this over here is the angle of the bar, and apparently these two angles are different. So if I want to produce a hinge force here to draw it to about to scale 57.3 degrees, that's actually just one reading by the way. So this is hinge force. So it is not along the bar. Many people may have the wrong idea that the hinge force has to be pushing along the bar, but it's not. It is not exactly along the bar. In this situation, it has to be above the bar so that the upward pull will balance downward gravity from the bar. So don't get confused between the physical angle between the bar and the horizontal, and this angle between the hinge force and the horizontal. Thanks.